we don't really know because again we've been playing with simulants, but um, anyway.
Is there a couple questions? I'll start with, so if you have an experiment where you're using like tens of milligrams and you're heating that up and then you're finding, okay, what's the, specific heat capacity or, you know, um, latent heat diffusion of this rock as it goes from solid to liquid or from liquid to glass or whatever phase transition you want to
Hmm.
do with it. Um, does that scale up linearly as you increase the volume, or are there weirder things going on?
Yeah, okay, that's a good question. So the short and easy answer is yes. The the better answer is first of all we're using yeah we do use very small quantities, and so it's really important that whatever we're looking at is representative of the larger thing. So for example, if I was going to measure the heat capacity of a granite, I wouldn't crush the granite into millimeter sized chunks and then just put a couple of them in because I might just have two pieces of quartz or two pieces of feldspar, and what I need is a mixture that's representative of the quartz, the feldspar, the mica, whatever else is in there. So I would powder the sample really finely and then take a scoop that was still only 20 milligrams, but maybe had, hundreds of grains of powder, and in which case it should be representative. So that's one issue, and that's kind of that's an issue that it's our responsibility to figure out when we're doing these experiments. Then there's the application part, and there it's the responsibility of whoever is using the data. Um, because when we do a measurement, we do it at a fixed heating and cooling rate, usually something like 20 degrees per minute. Um, the faster you heat, the stronger the signal. So that's good. You get a better signal to noise ratio. But also, the faster you heat, actually, there's a thing called thermal inertia, which is, it basically takes a bit of time for the heat to actually get into the sample. And so, if you're heating really quickly, the temperature of the furnace is always going to be ahead of the temperature inside the sample. And so, if you measure too quickly, we usually find that our sample will melt or complete melting at a higher temperature than we think is the true melting point. And that's just this thermal inertia effect. So we're always careful to point out that all right, this is where we measured this transition, the glass transition, or the onset of melting, the end of melting. But if you were using a process that had heating more slowly, you would see these transitions happen at slightly lower temperatures. It's usually not a really big deal, but when you're talking about what temperature do you need to get to fully melt the sample, then it's quite important because whether you need to go to 1600 degrees or 1400 degrees, that difference is makes a big difference to how you design your furnace and how expensive it would be. Um, but then also, of course, if you have a lava flow, the hot, which is a lot of what we use our data for is in modeling lava flows, the whole lava flow doesn't all cool at the same time. Likewise, if you're making a brick, the whole brick doesn't cool at the same time. The surface has to cool before the interior can cool, and you might have different temperature time histories for different parts of the same brick. And the temperature time history is going to determine whether crystallization happens at all or whether it's glassy. And then if it does happen, it'll determine what size the crystals are. And that in turn will determine the strength and physical properties of that brick. So anyway, so there's lots of detail here, which I enjoy thinking about. But yeah, so you have to be careful, because we're making measurements on very small things. I can tell you a lot about that very small sample. There are other things that it's not my job to actually figure out the thermal history of different parts of a brick, but it's definitely my job to help the people that are doing that make sure that they're modeling the brick appropriately.